Today I want to give to you a bit of an overview of how we developed an HPC software and developed a corresponding continuous integration workflow for that software, trying to first start from our own hardware, then more and more incorporating existing HPC resources at our computing center, and kind of what are lessons to be learned, what are different approaches that we can take, and also what are things that we need from HPC operators or computing centers to be able to use them for continuous integration in practice. So this is work that has been done jointly with Terry and Michele. Terry now left our group. Since then, our group also moved to Munich. So we are no longer all at Cultural Institute of Technology, but Michele is still there, and he's been doing a lot of the work on the custom executor that I'll be talking about in a bit. So what do I want to show today? First of all, brief introduction into the software that we're developing, so you understand what is our scope and what problems are we dealing with, what kind of hardware do we need. Then why do we even do continuous integration for those people who are not yet familiar with it? A brief aside about container management or container image management. So we are dealing with different configurations for which we want to run. Then we are specifically using GitLab runners for our execution. So I want to briefly introduce how they work and how we can move them and how we can use them on HPC systems. And finally, I want to show what approach we took to running on an HPC system, and also as kind of a final topic, how we managed to optimize the turnaround times, which are often an important thing if you have a lot of work happening at the same time and people want to get their code merged. Okay, so briefly, what is our software? Ginkgo is a sparse linear algebra library that is developed in C++ and has backends for all the major GPU vendors except for Apple, and multi-core OpenMP, plus a reference backend for validation. And we want to, of course, be able to test on all of those different hardware architectures that we support. And for that, we are using continuous integration as kind of a automated workflow. So what do? Every time we commit some code, every time we want to merge some code into our development branch, we run a set of automated tests. So first, we run some build tests, then we run some test executions, then we do some code quality checks, and finally, we do some deployment of the documentation to our GitHub page, so we always have the most up-to-date version of the documentation. So basically, what this does is it gives us a lot of trust in making bolder changes about our code, because we always know that our develop branch is going to compile and it's not going to have any failing tests. We know that we can make larger scale changes and trust that we are not breaking anything fundamentally. And also, as I already mentioned, we are not just running compilation tests. We can also run linting, static analysis tools, coverage tests, and all the kind of code quality measurements that you can use to see which parts of our code are, let's say, under-tested or under-evaluated. And of course, the documentation deployment I already mentioned. So in the end, this is how this looks on our GitHub page. Basically, we have a link to the latest documentation that is always being updated every time we merge our code. We have currently a failed pipeline, which is due to some CI runners being down. And we have some code coverage, numbers, some maintainability and reliability ratings from a static analysis tool, and some additional information from another static analysis or runtime analysis tool that we're using for evaluation. So why do we want to do HPC? Why do we want to use HPC systems for CI? Basically, our software is built for HPC. Even though our main focus is running on a single node, we still need to be able to use the hardware that is available there. We have AMD GPUs, NVIDIA GPUs, Intel GPUs even sometimes, and of course multi-core CPUs. And nowadays, people are also starting to use ARM next to x86. So we want to be able to test on all of these platforms. And many computing centers already have testbed platforms that provide all of that hardware. But we, of course, as like a small developer group of maybe like 5 to 10 active developers on the software, we can't afford to do all of that ourselves. It's a maintenance effort, it's a cost question, and also it's just a waste to not. It's a 25-minute talk. It's a 25-minute talk, not 15 minutes. Yeah, thanks. And so we can't afford to do that all ourselves. And the hardware would be underutilized if we weren't using it all the time to run CI. So it would be a waste to buy all that hardware, and it's only being used when somebody of us develops it. So it's better if that is actually happening in the context of an HPC center. Oops, sorry, my timer got lost. Okay, so. Now, what are the important components of a CI system? The biggest thing that everybody's talking about when doing CI is containers, that you want to have a reproducible environment which is tightly controlled. You can't modify anything persistently. Instead, you're always reset back to the same environment where you have a fixed set of compilers, for example, a version of GCC or Clang or a Microsoft compiler, and a set of libraries like MPI or any kind of runtime libraries, and also different environments that you use for parallelization, like MPI, SYCL, OpenCL, CUDA, HIP, and all that stuff. And of course, because we also want to run static analysis, we need some environments where we can run these tools. So typically, we also include our static analysis tools inside the containers themselves. And the nice thing is also these containers can then be shared on things like Docker Hub, GitHub, the container registry, and stuff like that, which allows other people to pull down these containers and reproduce test failures, reproduce development environments for themselves. This can not just be used for continuous integration, but also for development itself, which is also kind of the question that came up in one of the previous talks. But this is, of course, not always easy on HPC systems. So the nice thing is that we have a stable environment that we are building our software that doesn't change from job to job, but it's always the same. And if the developer needs to reproduce an error, they can just drop down into the container and figure out where that issue is coming from. So what are the common environments there? Of course, most people know Docker. If you've heard about containers before, Docker has a very popular and easy to use language to build images, and it's convenient to share them because everybody's using it. And there are lots of images available that you can build upon for all the different operatings or all the different Linux distributions, all different sets of software packages, and so on. And the most important thing for us is there's native support in the runner that we're using for our CI execution for running inside Docker containers. But if you want to use Docker, you need to install something as a system daemon. Docker itself has kind of root access to the system, so this is a security concern that operators will probably not want to give full access to the users based on. So what's an alternative in the HPC system, HPC environment? Singularity, or nowadays partially renamed to Aptainer, provides an alternative to Docker that can run without any root access to the system. So it can run entirely in the user space and uses some modern kernel features. And it can use Docker images, pull them down, convert them into its own internal format. But then you can just use it as you would use Docker. And it's even simpler in some cases because you don't need to create a container. You can just run inside the image as kind of a read-only file system with access to some select files that you want to give access to. So the nice thing is, because it came out of an HPC environment, NVIDIA and AMD GPU support is already built in, and the AMD GPU support also accidentally gives Intel GPU support. Only the kind of sad thing for us is that GitLab Runner has now a limited set of executors that it supports by default, and they will not be adding any new ones. So we will not be getting a native support for Singularity Obtainer in GitLab Runner, but there's still some extensibility that we can build upon to make this work. So the reason I'm mentioning Obtainer Singularity here is that like in a probably somewhat selective but still a big survey about the usage of containers in HPC, there was like a large majority of people using Singularity either on their own systems or on HPC systems, with Docker or Podman or others coming way behind because of the aforementioned issues with making it available to users. So now, how do we actually build these images that we can use inside the containers? The nice thing is that we can also use the same workflows that we use for developing code for creating and deploying those images. So just like we're developing code, we can have the Docker files for generating the code inside a repository that we version. And once we do a merge request, we run all of these pipelines to build the different containers and run some tests on them. What's a very useful tool there, for this is the HPC container maker, which was provided by NVIDIA, and now also has versions for AMD's software environment, which provides a rich framework of tools written in Python to create kind of parameterized Docker files that you can then build into actual container images. And basically, just to make sure that everything is working, we still do some functionality tests every time we build an image. And once that image works, we can deploy it to Docker Hub or any other container registry. And that's what we've been using for quite a while to make our software work well with the environment that we have. So how does such a CI workflow look if we're looking at GitLab? So basically, we have a build server where a persistent service is running all the time and checking repeatedly for new jobs. So like every few seconds, it asks the GitLab API for if there are any available jobs to be run for this runner. And once a new job comes in, the runner can then, if necessary, pull down the container images that are used for this job and then execute the job on this build server itself, and then report back the results to the GitLab API. And for the user, this is then observable inside the web page. For example, here you get a job log that tells you what are the different steps that were executed, what was the output, and did the code pass all the checks inside the CI job. Now, if we look at how people use an HPC system typically, this is very, very different. So we have a user that needs to log in into a login node, which is usually a very limited resource compared to what a compute node can do. If you want to actually do computations, you need to allocate some resources on a compute node, especially if you want to use GPUs or other accelerators. You need to explicitly send a job to a compute node, and all of that happens through a batch system like Slurm. And this doesn't easily translate to the whole GitLab runner issue because we cannot persist anything. We cannot persistently execute anything. One major thing since some IT security issues is that most centers nowadays use or require two-factor authentication, so you can't just log into a system via SSH and run something, but you always need to copy over some code that you get on your phone. And also, like the interaction through Slurm is not really easy. You mostly need to go through the file system or through interactive jobs, but all of those are difficult to handle. So what are existing approaches that other people are taking to CI on HPC hardware? In the Exascale Computing project in the US, they developed the Jacamar CI system, which is basically for their large-scale software projects and so on, a GitLab runner that runs on some system inside the compute cluster and is able to dispatch jobs to Slurm or similar But everything is happening in a centralized fashion. So they, like the maintainers of the system, maintain also the Jacamar. They register all the runners, and once a job comes in, it has to be authenticated, to be downscoped to the right user, and then it gets executed inside this unprivileged context, which is actually supposed to happen if you want to have a secure approach to running CI jobs. This is really nice if you have a big computing center which runs a lot of CI for different projects, but it also means that you need to cooperate things with the operators for the HPC systems, which means that there needs to be enough interest in running CI on these systems, and that can sometimes be hard to argue for. And also the setup itself is kind of complicated because it has a lot of moving parts. We need to do the downscoping and the handling of permissions and so on. And we need to do the scheduling via Slurm, and we need to set up the job environments and so on. So what else can you do? People can, of course, also buy their own dedicated hardware. But as I mentioned before, even though we then have full control over everything, we also need to maintain the software, maintain the hardware, and this can often be quite a significant overhead on the developer time. And while it's nice that we can use this software also as use this hardware as a development machine at the same time, we will often leave it idle because it can't be shared easily with other people who are running their kind of HPC jobs. So what do we use instead? What did we start off with? So kind of the first step that we took was instead of trying to do everything centralized, we wanted to do things from a user-initiated side. So what this means is that we built a so-called custom executor for GitLab that for the GitLab runner that then basically runs on the login node and communicates through the file system with the compute node, dispatches jobs through Slurm, and basically on the Slurm side, we have kind of a custom queue that is waiting for new jobs and waiting to be told that I'm done with my execution. So what is happening? The GitLab runner is running on the login node. It calls Slurm it executes Slurm jobs if necessary, and on the compute node side, we are running all the commands that are written through the file system, and we write our job log output again into the file system, which then the GitLab runner on the login node can read. But as you can imagine, this is very complicated and also very error-prone because there's a lot of things that can go wrong in a distributed file system. So this was kind of our first step, which we've been using for a while. But we then wanted to get away from because it doesn't cleanly work across all the systems that we've been using. So one side note here is that in most cases we had quite a lot of compilation work to do, but the tests themselves were very fast to run. So what we started doing also to kind of save on our budget because we were using a normal HPC project for that, is that we split the execution between compilation in a CPU-only node and test execution in a GPU node. But that meant that we needed to persist data between the compilation and the execution, and that turned out to be somewhat of a problem because we often had to deal with file system issues and related things that we were kind of trying to get away from. So this was an interesting concept, which also worked quite well in some cases, but we are now moving to a different approach because this turned out to be more interesting. So what is the nicest way, the cleanest way that I could have a GitLab runner interacting with the Slurm queue? So we have been thinking about this for quite a while, and the easiest way that we could come up with is to be able to directly submit a GitLab runner, a single job to be executed by the GitLab runner to Slurm on a specific partition. For that, we needed to do some modifications to the actual GitLab runner source code, but those are now merged into the source code, so everything works fine. And we just need to manage everything around that. So what does that mean? Every time we find a new job, we need to submit a matching Slurm job. So we can't use GitLab Runner directly anymore. Instead, we need something like a higher level runner that checks for new jobs and just executes a specific command submitting things to Slurm every time we find a new job. So this is basically how it works. Instead of having the GitLab Runner on the login node, we move it to the compute node, and we are able to run everything on there instead of on the login node, which also kind of reduces the load on the login node. To make that work, basically, kind of a side note, which we haven't talked about so far. Docker is natively supported, but if we want to use something like Aptainer with GitLab Runner, we need to use the so-called custom executor. So for that, we have different stages. In a configuration stage, we just give some feedback to the GitLab Runner info. Prepare can pull some images from a registry if necessary. The run stage is actually running the different steps of a CI job, and the cleanup stage then just gets rid of all the temporary files we created. And now, how does this meta runner that I mentioned work? Basically, we need a process that can, every time we find a new job, dispatch a certain command to a Slurm queue. So luckily, as kind of a CI setup, our computing center allows us to have lingering user services on the systemd side that can basically run on a login node even if nobody is logged in there. And that is what we have been using also for regular CI, but now we are moving forward to using that also for this kind of higher level CI on the compute nodes. But we can't use a nice feature like the webhooks to notify us of new jobs. Instead, we just need to repeatedly poll and check if there are any new jobs to be executed. And that also means that because we have different hardware architectures we want to execute, we need to kind of switch between different Slurm queues and different parameters to be passed to the GitLab Runner. So that because normally you need to maintain all of your GitLab runners via a web interface, this was kind of too much overhead for us. So now we have an automated registration and deletion of runners based on configuration changes that we do with this meta runner. And this is kind of where we are almost at now. So the project is not 100% in a polished state yet, which is why it's not published there. But soon it will be published behind this URL, because when I originally submitted this talk, I was hoping to be able to be done with this, but other things got in the way. So that's kind of the we're almost there message I'm trying to give there. And a lot of these discussions also were influenced, and lots of these ideas were influenced in discussions with Gerald Ragianti, or Jerry, who had kind of the same idea independently of me and worked on similar ideas just for the GitHub runner or GitHub Actions instead of GitLab. Okay. And so basically just to finish this off, what do we need from systems operators to be able to run HPC CI jobs? Kind of what is the minimum requirement that we need to be able to do? We need either some lingering or scheduled processes that can repeatedly poll the GitLab queue, or we need some automated CI, automated SSH login capabilities, which are often conflicting with the two-factor requirements. And of course, the compute nodes need internet connectivity, which is sometimes an issue, but in most cases, it's possible to configure this somehow either via proxy or via Slurm parameters, and then we can use that directly. And finally, there needs to be some support for a container runtime that runs from the user space, so we can use that safely as kind of a basis for our job environments. And of course, there are a few security considerations to take into account if we're talking about this. So the meta runner that I mentioned would only be executing the same Slurm command every time. So there's no way to inject commands on this side. But the job that is being run on the compute node then needs to pull the repository. So any kind of code that is being executed as part of the CI job would be pulled from the repository. So there is some danger of people injecting code in there, but the security model of GitLab or GitHub is already is already geared toward that. So we're able to prevent like arbitrary people just pushing code and triggering jobs that way. And also the custom executor will then execute the code that is inside that repository, but we can kind of limit the danger of this because a container runtime like Obtainer, even though it's not built for security in kind of a first step or first priority, it still restricts access to most of the features on a compute node. So we cannot really do any dangerous things except for just computing things. Anyways, yeah, that's all I wanted to say. I had another section that I just kept in case I have enough time. But I think this is just it from my side. And if there are any questions, I'm happy to answer them.
Shall we thank Tobias and colleagues? Yeah, I must say there has been a lot of interest, a lot of questions.
Yes.
So let's see how it goes. One of the popular questions is, why not make the repo public before it's ready?
Oh, because it's basically just, like it has a lot of issues with like the configuration generation that I mentioned, the automatic generation of runners and registration of runners and deletion of runners is very like unstable. And I don't want to put something out there that might mess up your repository. So I will just keep it there until everything can be pushed to the public repository. But I'm hoping to be able to clean that up in the next week. So
brilliant,
yes.
Thanks. Another one actually is, okay, it's changed. Okay, so the question is, distributed file systems such as Lustre, I don't know if I pronounced the word, distributed file systems such as Lustre are really not ideal for building source code.
Yes.
Things can go quite slowly.
Yes.
Any suggestions for making
yes,
it quicker?
This is basically also one of the reasons why we don't want to do the split execution that I mentioned, because all of the compute nodes, if we're doing single node builds, they have local scratch space that is perfect for doing things. So you don't want to run on, you don't want to do everything via the distributed file system. Like if you run on a single node, either via the custom executor or via a GitLab runner directly running on that node, you can already just use the local scratch space and kind of mount that into the container that you're using as the build folder. So that's also what we've been doing. Just if you want to do a split execution where you split between build and test, you need to persist your data, and that's where a distributed file system is necessary. But that's also the reason why we didn't do it in the end, or why we're trying to get away from it.
Brilliant, thanks. Next question. Does requiring outbound network access from the compute node to fetch jobs from GitLab cause problems?
So the HPC systems I'm using, we don't have any problems with that because the login node is set as a gateway, or one of the nodes is set as a gateway. The main issue there is that basically you would need some way some kind of proxy to forward all the requests to the GitLab API, because we are running things on the compute node directly. If we want, like there's basically two options. Either we do things on the login node, which hopefully has internet accessibility, and then we need this complex custom queue set up to pass information to the Slurm job via the distributed file system. Or we can do things directly on the compute node, then we don't need this complex setup, but we need internet connectivity on the compute node directly. Yeah. But also the builds themselves sometimes need to pull things from GitHub or so, kind of dependencies or similar stuff. So it might not always work with the compute node without internet connectivity.
Brilliant. Okay, so this next question is actually three in one. Okay, the one, well, I'm trying to follow the likes, the popular ones, and it keeps changing. So that's very interesting. Okay, so the next, okay, let me get this one. Is this tied to a single person's account on the HPC system? Have you been able to get a project login?
Yes, so basically, because we were employed at our computing centers, it was possible for us to get a service account, which is kind of an account that is not tied to a specific person, but managed by a group of people, or a single person is responsible for it, but we can share access to it or something like that. So this is this is, I guess, more of a policy question than of a technical question. But you can either do it via a specific user, but that means if the user is like sick or out or whatever, then you won't be able to fix your CI if it breaks. But the other one, of course, requires some policy that allows you to have shared accounts on the HPC system.
Brilliant. Okay, another one. Can you describe the effort required to deploy this on a new HP system?
Yes. So if everything is fixed with this meta runner, then the effort would be basically you need kind of a template configuration that is supposed to be used for all the different partitions that you want to run on. So this is similar to a normal GitLab runner configuration. And then once that is running, you basically just need to set the Slurm parameters. So like set the Slurm command line that is supposed to be executed when a new job arrives. And then then it automatically gets dispatched. And of course, you need to set up like any kind of lingering process or a scheduled process that repeatedly pulls for new jobs to kind of have this meta runner work. If you want to like go with any of the other approaches, the effort level is, I think, similar. So some of the projects I've seen basically provide you with some tools that automatically generate all the GitLab configuration files on the system, and you only need to configure the service. But this, of course, varies a lot between how the different computing centers do things.
Brilliant. Time's up. But I must say that there are a lot of questions in there, so I expect a lot of people approaching you. I think there's been a lot of interest. Shall we give Tobias and his colleagues a round of applause?